Next, we'll proceed further. We'll proceed with the concept of odd functions and even functions. So, odd functions are functions which are so odd function, a function f of x is said to be an odd function if f of minus x, if f of minus x is equal to minus of f of x. So if this condition satisfies, then it is an odd function. Examples of odd functions are f of x equal to x cube or any odd powers of x. So when you write f of minus x, so minus x whole cube, minus sign comes out, minus 1 whole cube will be minus 1. So you get minus of f of x. So this is an odd function. Similarly, if you have terms in a polynomial in which all the powers are odd, then it will again be an odd function. So f of minus x will be minus x power 5 here, then minus of x cube. So minus of minus becomes plus, then here x becomes minus. And when you take the minus sign common, you will get the original function. So now how does the graph of an odd function look? So the graph of an odd function is symmetric about the origin and lies in the opposite quadrants with f of 0 equal to 0. So graph of an odd function is symmetric about the origin. What does that mean? Here is the understanding of it. Whatever, say this at x, the value is f of x. At x, the value is f of x. So whatever be this length, this particular length. Now f of minus x will be minus of f of x. It will be minus of f of x. So this length will be equal to this length, but in the negative direction. It will lie in the opposite quadrant. If f of minus x is positive, then f of x will be negative, because f of minus x is equal to minus of f of x. So if the point lies in the first quadrant, then a symmetric point will lie in the third quadrant. Here is the example, y equal to x cube. Here you can see this is the graph. The violet colored curve is the graph of y equal to x cube. Now this length of the point B from the x-axis and this distance of A from the x-axis will be equal, but it is in opposite quadrants. So another way of saying that it is symmetric about the origin is this x comma f of x and minus x comma minus f of x. If you join by a straight line, it will definitely pass through the origin. It will 100%, it will pass through the origin. And origin will bisect the join of these 2 points, x comma f of x and minus x comma minus f of x. No matter what x is, you keep changing the x, and then this line will also keep changing. But the midpoint remains same. The midpoint remains same. That is the origin. So the origin bisects the chord joining AB. So that is the graph of odd function. Now let's look at even function. A function is said to be even if f of minus x is equal to f of x for all x belonging to the domain of f. So even functions will have, if it's a polynomial, it will be all having even powers. So if it has even powers, f of minus x whole square becomes x square. Similarly here it is polynomial terms with all even powers. So f of minus x will be f of x. Now graph of an even function is symmetric about the y-axis. Very important. It is symmetric about the y-axis. So x comma f of x and minus x comma f of x. This is f of x value here. So for x and minus x, the function value is the same. So now the graph usually is like this, or varieties of it. It will be symmetric about the y-axis. It need not be passing through 0, 0. It is not necessary. But it will be symmetric about the y-axis. So here is the example of y equal to x square. At x equal to 2, value of y is 4. At x equal to minus 2, also the value of y is 4. So it is symmetric about the y-axis. So about the y-axis, you take the image 2, 4, you get minus 2, 4. Another example of an even function is modulus function. Yeah, modulus function, y equal to mod x is this. It is equal to y equal to x when x is positive. It's y equal to x when x is positive, and it is y equal to minus x when x is negative. So these are the graphs. Now product of two functions, properties, product of two functions.
Can you scroll up once?
Yes.
A bit more.
Here?
Yeah. Okay, so done.
Okay. Done? Now properties, product of two odd functions or two even functions will be an even function. So product of an odd function and an even function will be an odd function. So here is an example. Let capital F of x be product of small f of x and small g of x. So replace x by minus x. You get f of minus x into g of minus x. F of x is odd. So you get f of minus x as minus f of x. G of x is even. So g of minus x will be g of x. So the product will have a negative sign. So you get this as minus of f of x. So it is an odd function. So this is an odd function. All right, just a second. Okay, next, just a second. What's happening? Yeah. Next. Now, this is a very important property. Very, very important property. Very useful. Every function can be expressed as a sum of an even and an odd function. So let f of x be any function. Then f of x can be written as f of x by 2 plus f of x by 2. Then we can add and subtract f of minus x you have added, and f of minus of f of minus x you have subtracted. So then you combine these two, f of x plus f of minus x upon 2 plus f of x minus of minus f of x upon 2. This component will be even, this component will be odd. You can see this. You replace x, let this be capital F of x, replace x by minus x, you will get f of minus x plus f of minus x. So you'll get f of minus x plus f of x by 2, which is f of x original. So it's an even function. Now g of x you write as f of x minus of f of minus x by 2. You replace x by minus x, you will get f of minus x minus of f of x upon 2. With a negative sign, you get the same as g of x. So this component is even, this component is odd. Okay. Next, periodic function. A function is said to be periodic if there exists a positive real number t such that f of x plus t is equal to f of x for all x belonging to d. Periodic function. So periodic function is a function that repeats itself after every interval t. So f of x plus t is equal to f of x for all x belonging to the domain. If t is the least positive value for which this equation holds, then t is called as the fundamental period. Now, if t is the fundamental period of f, then function is also periodic for the multiples of the fundamental period, for 2t, 3t, 4t, and so on. So periods of some standard function. Okay, of course, most importantly, we deal with trigonometric functions, period, but some of the standard functions, period, is this fractional part function. F of x is equal to fractional part of x, which is x minus modulus of x minus real part of the integral part of x minus integral part of x. This function is periodic with period 1. This is periodic with period 1. We will learn. We'll learn about this more also. So here you see, I'm plotting x minus floor of x. So this is the fractional part function. You can see its graph. I'll explain this function, this particular function in detail. Right now, when we are talking about periodicity, I'll just restrict here that you just understand that this is a periodic function. Soon I'll be dealing on this function in more detail. Okay, so this fractional part of x is a periodic function. Next, constant function f of x is equal to k. Now constant function is periodic with no fundamental period. It is periodic because for all values of for any value of t and any value of x, this equation always holds true. It is always constant. Value doesn't change. Whereas for other periodic functions like this one, you can see for a certain values of x, all right, for these values of x here, say half, 3/2, 5/2, 7/2, 9/2, 11/2, for these, and then minus half, minus 3/2, minus 5/2, so on. For these values, the function takes constant value half. For all these, the function value is half. All right. Whereas for constant function, throughout the values of x, the value will be the same. Let's say f of x equal to half. We can do that. Y equal to 0.5. So you get this line. Now close this. So you see, for this function is always constant. So no matter what the value of x is, the function value will be constant. So it doesn't have a fundamental period. Here it is a fundamental period. You have half, 1 as the fundamental period. After every 1 unit, the function repeats itself. The values of the function repeat. However, for constant function, you cannot say that it has a specific period. Next, algebraic functions are not periodic. This is the nature of algebraic function. Trigonometric functions, they are periodic. So you have already done trigonometric functions in your colleges, and of course those who have attended, I've covered the entire trigonometry in great detail. So trigonometric functions, sin x, cos x, cosecant x, secant x are periodic with period 2 pi. Tan x, cot x are periodic with period pi. Now sin x, cos x, cosecant, secant are periodic with period 2 pi, but when you square them, the period reduces to pi. Similarly, however, tan square, cot square, the period doesn't change. This is because of the nature of the graph, nothing to do with. So let's say we plot sin x. So this is sin x. Now we plot sin square x. So there's a way to set the axis. Ouch. Control Z. Okay. Okay.
Sir, we understood what you're trying to show, sir. It's fine.
I'm trying to show something else. Okay, I'm trying to change something. No problem. Okay, I'll do that setting later. I'll do it later. Now what I wanted to mark here, I can't mark on this program. Okay. Now what I want to show is like, of course, this is sine x and this is sine square x. You can see sine x repeats at every 2 pi. This is pi 3.14, 2 pi is 6.28. So after one full cycle, sine repeats. Sine square, of course, repeats every pi. So when you square sine and cos,
Sir,
mm,
is sine square x an odd function?
no, sine
Why?
square x is an even function. Sine x is an odd function. Sine square x is an even function. You can see it is symmetric about y-axis.
Yeah, so it's even, right? Sine
Yes,
square x?
sine square x is even.
Yeah.
Sine x is odd.
Okay.
Okay. Now, if you look at cos
So
x,
repeat the condition for odd function. If it's odd, it has to pass through the origin. Is that the
yes, yes, it is not compulsorily it has to pass through origin, but generally odd functions pass through the origin. If they are continuous, they will pass through the origin.
Okay.
And you can draw any line passing through the origin. All right, it will cut at 2 points, which will be symmetric from the x-axis. Okay. Now this is y equal to cos x. This is, I am now highlighting y equal to cos x. Okay. So this is this graph cos x. Cos x is an even function. Now when I do cos square x, now periods, we are talking about periods. So period of cos x repeats every 2 pi. 0, this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi, 6.28 roughly. So cos x, the whole curve pattern repeats every 2 pi. So period is 2 pi. Cos square x, however, the period is pi. Cos square x period is pi. After every pi, every 3.14, it repeats itself. So what's happening is the negative portion, because of the square, it goes to positive. All right, the values get squared and goes to the positive axis. Okay, so what have we observed is for sin x and cos x, when you square, the period reduces from 2 pi to pi. However, for tan x, that doesn't happen. This is tan curve. The range is minus infinity to infinity. All right, and it is periodic with period pi. If you see how it is repeating, now this is from minus pi by 2, minus 1.57 to 1.57. So from minus pi by 2 to pi by 2, you will get one full tan curve. And again it repeats from minus pi by 2 to 3 pi, pi by 2 to 3 pi by 2. It repeats. And then 3 pi by 2 to 5 pi by 2. Again it repeats. So period is pi. Period is pi. Tan of pi plus x is tan x. We know that. We know that relation. Tan of pi plus x is tan x. So, but when you square, what happens? You see the green curves. When you square this curve, the negative portion goes to positive. And of course, because of the square, there will be slight change in the values like this. And so this will be the green curve, and that is tan square x. Okay, whereas this brown curve is tan x. Now you see this tan square x is also repeating every pi. It is not becoming pi by 2 because of the shape of tan x. Okay, because of the shape of tan x. Similarly for cot x. So that is what you need to be careful about. That when you square trigonometric functions sine, cos, cosecant, secant, the period from 2 pi reduces to pi. However, tan, cot, which are periodic with period pi, even after squaring, the period remains pi. And of course, if you take modulus, you're not squaring, you just take the modulus. For modulus, the negative becomes positive. Just see this one. Let's say I'm editing it. So absolute value of tan x. Absolute value of tan x. This is the absolute value of tan x, the green curve. See this? This is tan x, absolute value of tan x. The positive part will exactly match the tan x because it's not getting squared, the values remain the same. The negative portion gets reflected upwards. So this is your tan mod tan x, absolute mod value of mod tan x. Okay, so same mod sin x, mod cos x, absolute values, you can do that. So these are trigonometric functions, they are periodic. Now properties of periodic functions. If f is periodic with period t, then you multiply f with a constant, you add or subtract to x a constant. To the function value itself, you add and subtract a constant. The period remains unchanged. The period remains unchanged. Okay, rather it just moves up and down. For example, here let us take simple sin x or cos x, let's say. Now I add cos x plus k. All right, cos x plus 2. If I do cos x plus 2, the curve has just moved up. And if I do cos x minus 2, you see what happens? The curve moves down. All right. Now, next, suppose so period, the repeating interval remains same. It doesn't make any change to that. When you're adding to the function a value, the whole function, the values get added to the entire function. The entire function moves up, or the entire function moves down depending on the sign. However, when you add, listen very carefully, when you add, let's say pi by 2. See what has happened. When I added pi by 2, cos x graph shifted to the left. And the same when I do subtraction. The cos x graphs will shift to the right. In fact, I should be able to insert a Yeah.
Sir, can you show it again?
Yeah, I'm showing it. I'm trying to show it again. Hold on. Slider. Yeah. Okay. Slider is here. I'm showing you, just observe this very carefully. Cos of x plus a. Now, see, I'm sliding this. See how the graph is moving? Cos x graph. As the values of a are changing, what I'm sliding is cos of x plus a. So when a values are positive, it will slide to the left. When a values are negative, it will slide to the right. Okay, got it? So when so what do you understand is, when to a function you add a constant or subtract a constant, when you add a constant or subtract a constant, you will get a, just a second, sorry. Sorry for the distraction. The function will move up or down, but within the variable, to the variable x, not the function value, to the variable x, you add or subtract a constant, the graph will move either to the left or to the right. Okay, so period remains as it is. The repeating portion remains at a constant distance. So after every interval of t, the function repeats itself. So that doesn't change. That's why the period doesn't change. Similarly, now if you multiply with a constant, let us delete all this. Okay, simple. I take sin x. Now with sin x, I take 4 multiplied by sin x. What has happened? The period has not changed. The interval in which the graph repeats has not changed. What has changed is the amplitude, the maximum and minimum. So 4 times sine pi by 2 will be 4. So, and then when I change it to 1 by 4, let's say 1 by 4 is 0.25. The period doesn't change, but the amplitude changes. Okay. So that's what we have to understand, that periodic functions, they do not get altered whether you multiply by them by a constant or add or subtract the constant to the function. What changes the period? Very important. What changes the period is, to the variable x, you multiply a constant. When you multiply a constant to the variable, the period becomes the original period divided by modulus of c. If it is -2, it will become t by 2. If it is 2, it will also again become t by 2. Now this k times f of cx plus d, d will not alter the period, k will not alter the period, but this c will alter the period. Okay. So for example, this is sin x. So this is sine x. Now let us do sine 2x. This is sine 2x. Again, this is sine x. This is sine 2x. Turn off this slider. Okay. This is sine x. This is sine 2x. So what has happened? The period that was this one cycle which took 2 pi. Now within that 2 pi you have two cycles. One maximum, minimum, again 0. Again it is repeating itself. That means the period has reduced by half. Now if I change to 3, the period will reduce by 1/3. So within one cycle of the sine x, sine 3x has 3 cycles. Understand? So period reduces by 3. Now when I add 4, make sine 4x, the period is reducing by 4. So 4 cycles you get. So that is what happens. Now last part of periodic functions. If f1 and f2 are periodic functions with periods t1 and t2 respectively, then what if I add two functions with different periods? So the period will be the least common multiple of t1 and t2. LCM of t1 and t2. Of course, there are some exceptions. This is very important. Okay, now let me ask some simple questions. What is LCM of say 3 and 4? What is LCM of 3 and 4? Trivial question. Answer? 12. So 12. Least common multiple of 3 and 4 is 12. Okay. Now, what is the least common multiple of LCM of 2 and 6?
6.
6. Okay. Next question. What is the LCM of 1? Okay, 2 and pi.
Not defined.
Just a second. So why not defined?
Sir, because the LCM of a rational number and irrational number does not exist because pi is irrational.
Very good. See, what do you mean by LCM? You write down multiples of 3. 3, 6, 9, 12, 15, 18, so on. What are multiples of 4? 4, 8, 4 added twice, 4 added thrice.
16, 20.
So least common multiple is, this is the This is a multiple, this is a multiple. This is the least common. After that, there will be greater common multiples. 24 will be one. You will get that. But this is the least common multiple of 3 and 4. Similarly, for 2 and 6, 2, 3, 2, 4, 6, 8, 10, and this is 6, 12. The least common multiple is itself the number 6. However, now 2, 4, 6, 8, 10, so on. These are multiples. The multiples of pi are pi, 2 pi, pi plus pi, pi plus pi plus pi, 3 pi. Okay, the third multiple, fourth multiple, fifth multiple. Is there a possibility? Because all these are rational numbers. In fact, they are integers. And these are irrational numbers. Pi is irrational. 2 into pi is also irrational. 3 into pi is also irrational. 4 into pi is also irrational. 5 into pi is also irrational. So LCM of a rational and irrational does not exist. So that's why we have to be extremely careful how we write the periods of functions. Okay, so if the period of one function and another function, one is rational and another is irrational, then you don't have a common multiple. So the sum of those two functions will not be a periodic function. Now, another important catch with this functions, one exception is there. Let's say T1 and T2 are of same type. That is, both are rational. B, either both rational of same type. That is rational or irrational. Okay, I just leave it there. Both. That is both rational or both irrational, doesn't matter. Now, if the functions, if f1 of x and f2 of x are complementary functions, then the period can be, you have to verify. Okay, period will be for f of x, the period of h of x here, sorry. The period of h of x will be LCM of T1 and T2 by 2. We will do examples of this. All right, these are some important points I wanted to make. Problems. Okay, I'll take some problems. What is period of sine 3x plus sine 4x? Okay, what is the period of this function?
Two pi.
Okay. The period of sine 3x is?
2 pi by 3.
Yes, 2 pi by 3. Period of sine 4x is 2 pi by 4.
Okay. Yeah.
All right. So this is basically pi by 2 and this is 2 pi by 3. 2 pi by 3 is like 120 and this is 90. So what is the least common multiple? You cross check. So 120, 240, 360, next 480, so on. And then other one, pi by 2, 90, 180, 270, 360, then 540, so on. What is the least? 360. Okay. So period is
2 pi.
good. Period is 2 pi.
Sir, I have a few questions based on this topic.
Wait, I'll give you more questions. Right. What about this one? F of x is equal to mod sin x plus mod cos x. Find period.
Pi by 2.
So you know it. How?
Sir, because period means f x plus t, right? So if you substitute x plus 90, we'll get cos x. And if you substitute cos x plus 90, we'll get sin x. So
What is the period of this? Pi. What is the period of this one? Pi. LCM of pi and pi is equal to pi. But now you have to verify. The sin x and cos x are complementary functions in this sense that sine of x plus pi by 2 is equal to cos x. And cos of x plus pi by 2 is minus sin x. Okay. Cos of x plus pi by 2 is minus sin x. However, because of the modulus, so f of x plus pi by 2, what do you get? Is mod of sine of x plus pi by 2 plus modulus of cos of x plus pi by 2. So this is modulus of cos x, no problem, plus modulus of minus sin x. So modulus of AB is mod A into mod A. So mod minus 1 into mod sin x. So it will be sin x. It is the original function. So although by LCM, this is pi, but your period here will be half of LCM of the two periods. So it is pi by 2. Okay, because sin x and cos x are complementary. All right. Same, exactly the same reasoning for this question. F of x is sine power 4x plus cos power 4x. Of course, there is an alternative to do this. I'll show that alternative also. Period of sine power 4x plus cos power 4x. Okay. This can be written as sine square x the whole square plus cos square x the whole square, which is sine square x plus cos square x the whole square minus 2 sine square x cos square x. What did I do? A plus B the whole square minus 2AB will give me A square plus B square. That is what it is. Now the sine square x plus cos square x is 1 minus. Now I multiply and divide by 2 to make this as 4. So I get 2 sine x cos x the whole square. So I get 1 minus half sine square 2x. Now from multiple angles, we know that cos 2a is 1 minus 2 sine square a. So sine square a you can write as 1 minus cos 2a upon 2. Okay. So 1 minus half 1 minus cos 2a, that is 2 into 2x cos 4x by 2. So I get 4 minus 1, 3 plus cos 4x, or 3 by 4 plus cos 4x by 4. So now we have seen that when you add a number to a function, it doesn't change its period. You multiply a number to a function, it doesn't change. But when you multiply a number to x, the period changes. So period of this is cos x period is 2 pi divided by the coefficient of x, 4. So you get pi by 2. So this is one way to do it. Of course, the alternative is just use this f of x plus pi by 2 for sine power 4x and cos power 4x. You will get the same period, pi by 2. Okay, got it? So I'll stop here. I will share with you an assignment which has domain, range, periodicity, and even odd nature of functions. It is not an objective question. It is just some practice problems. You all try that and you can clarify the doubts. All right, Prisha and Mahita, you had doubts.
Yes, sir.
Harshita, Harshita, I'll address your doubts tomorrow.
Okay, sir.
Okay, I've got the solutions to the problems you asked. I'll
Okay, sir.
address.
Thank you, sir.
Okay. Okay. Mahita, you have questions on what?
Matrices, sir.
How many questions you have?
So I sent you 4 items, sir.
Prisha, do you mind attending this?
Yes, sir, I can attend it.
Okay. No. Okay. Stop the recording first.